So now we found the errors that the list always inserted back, because this item is never changed, location always 0. That's why the list always compared to A, or the first index. So we need to move this to change inside the loop. Right, because whenever location plus plus change, it should take new values to compare inside the loop. And once we fix that, we run the test. It should returns insert in order now. Right? A, B, C, E, F, and D should find a location to insert and shift the rest. Okay, so we can look at implementing ADTs by copy or by reference. Right. Next, when designing an ADT, we have a choice about how to handle the elements by copy or by reference. By copy, the ADT manipulates copy of the data used in the client program. Making a valid copy of an object can be a complicated process. So by reference the actual elements passed to it by the client program. So this is very common use approach. The valid copies of an object are typically created using the object's clone method. Classes that provide employee method must indicate this to the runtime system by implementing the clonable interface. So drawbacks: copy of object might not reflect up-to-date status of original object. Copying objects takes time, especially if the objects are large and require complicated deep copying methods. Storing extra copies of object also requires extra memory. By reference. Because the client program retains a reference to the element, we say we have exported the contents of the collection ADT to the client program. So ADT allows direct access to the individual elements of the collection by the client program through the client program's own reference. Drawbacks: we create aliases of our elements. Therefore, we must deal with the potential problem associated with aliases. So this situation is especially dangerous if the client program can use an alias to change an attribute of an element that is used by ADT to determine the underlying organization of the elements. For example, if it changes the key value for an element stored in a sorted list. I think you're going to understand when you look at example here. So let's look at the left side is when you do copy approach. Right side is when you do reference. So we have the list, the name and the wage, Doug, Jane, and Jen, 230, 120, and 127. Now if I do store the values by copy the values into a list, this is sorted list, so we're just going to put Jane sorted by wage, right? Jen and Doug. But if you do store by reference, you just use the pointer to the location where the object is. Now, when you do update Doug wage to 125, when you copy, store by copy, then the values on the list is not updated. So that's the drawback, which is the list not up to date. This value stored in the by reference is just point to the location where Doug is. When the value is updated, then the list is also have the latest value, right? But the list is no longer sorted. That's a drawback because it's sorted by wage. So how would we copy then? How would we store the data? By copy or by reference? It depends. If processing time and space are issues, so we go do by reference. If not too concerned about the time and space, we do by copy. Alright, so now we understand when to use each. This is about indexed, right? List if you use an array. The application that we can use, we can make a game for poker, golf, music. You can pretty much just look into the details of this book, of this code in the book, okay, by yourself. And the next topic is about the binary search algorithms that make your searches faster by divide time in half. Okay, so like searching a phone book, like we're looking for a phone number for David, you just go into half, right? Instead of just starting from order A, B, C, D, and you just flip until you get David. So that search is faster than do linear search. Like for example, we're looking for bat, we just jump into the middle, dog, we know that it's going to be in the first half, so middle of first half chicken, first half is cat. Oh, we not find bat, then we do only 4 times instead of spend time 10 times. And we said bat is not on the list. And we pretty much just do the iterations and start the location, divide by 2, right? And start to do compare to. If the compare result is equal to 0, we found it break. Else that means we not finding it. It's less than, we change the index of the last to the first half, location -1, and start a little bit again. Else that means on the second half we change the index of the first half to location +1, and just loop again. Let's keep doing that until we find it and break out. So that's the logic, and the big O of this is going to be lock-in efficiencies. We can also use recursive method to do this. Just create a recursive find, right? Put the comparable target, which is the values that we try to find, and start from location to location. So find, start to pass the target in, and target going to pass into target elements, but we cast it to comparable because we have to make it compare to, right, in order to find is it greater than or less than. So now we start from locations to 0, like the whole list, and to the end, which is the size -1. Then this is the same. If this is the best case, if from location happen to be to location greater than, that means we pretty much just recursive through the list already, and we're not finding it, found equal to false. Else that means we start to do compare. Start from the half location, get the compare result, because it's called compare to, which is -1 less like equals 0 or greater than. So if compare result equal to 0, that means we found it. Else less than, we just recursive call, but change the location to, right, from location first half, right, because less than to location -1. Else that means second half form should be location +1 to location at the end. Keep doing that until either not in the list or found breakout. So that's the recursive method. And we see that by doing the binary search, if efficiency is locked in, you can see if we have 10,000 data, only 14 times. But with binary, with linear, it's going to be 10,000 times to say we're not finding things in the list, which is too long. Alright, so that is the binary search, right? Now, for the list itself, we look at how to use array to implement, like example of add. We can also use linked list to do that. Alright, so order list and bulldog pen. Now, when we want to insert something, this is unsorted. It should be very easy. It could be anywhere in the list, either in front, like this, always insert in front, like stack, right? Models. Fine, just iterate to it, right? If we found, then we return true. Else, just change the location, keep everything, right? We need pointer previous to help. Remove. Once removed, we can just set the previous. The reason we need previous to help because we can set previous.setLinks to location.getLink. Like that. Once we found, remove. But if it's first node, that is only one node. List equals to location. Then we just remove it, right? And move the list to the next one. Because list point to the head of the list. Now, how about if we want to do sorted list? So, sorted list, let's look at the picture here. So, it has to be ordered, right? So, we want to insert count. We have to iterate to the list. We found it. This is location. But we need to rely on the previous location because we need to set the previous location dot setLink to the new node and new node dot setLink to location. That's how we break this into this image. That's how we insert. Right. Now the case is like if the previous location equal to null, that means like is the first node, is the first item, right? Then we can just set new node set link to list and list equal to node. New node. Let's say we said the list is empty. Now this is going to point to null, right? Let me use this. It's null. This is empty. And this is list. And we want to insert. So we pretty much just going to create a new node. This is a new node, right? And we said we also rely on previous pointer. So we need a previous pointer. So this is list, and we also have the same thing, which is a previous pointer. We have previous pointer in list, which is pointing to the list, null. Previous location equals to null. In that case, we create a new node, right? And new node dot set link to list, which is null. And list equals to new node. So pretty much we're gonna say this is the list. The set link point to list, that meaning that it's point to null because previously it was null. Right, and then list equals new node. So this is example, right? Another example is actually insert in the beginning. I show you that's when it's null, but this is when it's actually insert in the beginning. Like S should be before ant, and previous location is null, right? So that's why we have to go back. New node dot set link to list. So new node dot set link to list is point to list, and move your list to new node, right? List equals new node. So that's net scenarios.